Today we're going to go through Faraday's law. But before we do that, I wanted to actually show you how I can generate electricity using Faraday's law. In fact, I have a spool of wire here, a bit like a solenoid. You can imagine that this is a solenoid. I have a multimeter which will measure the voltage, or in other words like the electricity generated, and I have a magnet, and with just these two things I'm going to be, and this thing to measure it, I'm going to be able to generate electricity, which is pretty cool. So let me set this up and then we'll have a look. So what I have set up here is my multimeter. I put it into the voltage mode. I have my voltage probe set up across the ends of my solenoid, and let's watch what happens when I push my magnet in. You can see that as I push my magnet in, briefly there was a bit of voltage. And so that is electricity. I just generated electricity. This is exactly how they do it in a coal plant, in a hydroelectric plant. I just generated real usable electricity. If this multimeter was instead like a little LED, you would see it flash on. And let's see what happens when I remove my magnet. You can see that it also flashed, right? So that means that when I put it in, there's a voltage, and when I take it out again, there's another voltage. So why is that? And one more thing before we explore why that is. You can see that if I put it in, there's a voltage. If I leave the magnet in there, there is no voltage. So let's take all these data points, let's go and explore, and let's use these to explore Faraday's law. So what is Faraday's law? Well, we saw Faraday's law in action there. It seemed that when we had a change in the magnetic field over time, we created a voltage. So a voltage can be created when there's a change in the magnetic field over time. Now, this is actually a bit crude. Let's kind of go a little bit more in depth and understand more about the change in the magnetic field over time. There's a better way to measure the change in magnetic field. The problem with this formula is that it's not quite finished yet. We want to be able to quantify the change in magnetic field over time with more numbers. And so to do that, we actually need a new concept, and that is the concept of magnetic flux. So I've actually done a video on magnetic flux separately, where I'll go into more detail, but in essence, what magnetic flux is, the symbol phi is for flux, is equal to B times A. So B is your magnetic field strength, and A is the area that you're exposed to. And so you might be saying, well, why is that, right? Why do we define flux like this? Well, if you imagine flux is really a measure of the number of flux lines. So it's a measure of the number of magnetic field lines that you have. So as an example, I can show you that, for example, I might have, let's say 2 squares of equal area. Inside the first one, I'm going to have a very strong magnetic field. I'm going to have a very strong magnetic field, so a very dense series of crosses, right? Very dense. And the second one, I'm going to have it much more loose. And you can see here that quite evidently, it is our left-hand side one that has more flux, right? Because there's a bigger B. The B here might be, let's say, 10 Teslas, and here might just be 1 Tesla, right? So because we have less, we have 9 flux lines. Here we have maybe 100, many more flux lines than here. That's the more flux lines we have, the more flux we have, right? Another way of another way that we can increase the amount of flux, the number of crosses, is by increasing the area, right? So for example, I might have, let's say I have this one. So again, we have 2 squares of equal magnetic field strength, but what I could do is I could make this square bigger, right? I could make this square bigger. and the magnetic field would still be the same density, right? So, you know, it's like if I have 9 trees per hectare, you know, this farmer has 1 hectare, I have 4 hectares, I plant the same density of trees, still 9 trees per hectare, but now I have 4 hectares, so 9 times 4 is 36. You can see I have now more flux lines in this square than this guy had. So this guy has more flux, and this guy has more flux than this guy. That's magnetic flux. We're going to be able to measure the amount of magnetic field penetration through using this concept of flux. So what Faraday's law actually is that Faraday's law is this. Now let's go through a couple of symbols here. So what is this guy? This guy stands for EMF, which stands for electromotive force. You might say, whoa, Bob, what's electromotive force? Electromotive force is just a really fancy, kind of old-fashioned way of saying voltage. For all intents and purposes, at a HSC level, EMF and voltage are exactly the same thing. There's no difference. It's just the same thing. It's like saying, college and uni. It's the same thing, right? So EMF, voltage, same thing. Even at a university level, the difference is very, very pedantic. It's not something that you need to worry about. Over here, we can see that this is flux, right? So we have a change in flux over a change in time. So instead of just magnetic field, we're actually going to be more precise and measure it with the change in flux. Okay, so this is Faraday's law. And that's it. So we're actually going to see a couple of examples now to see exactly how Faraday's law is going to work. So let's have a look at this question. Determine the EMF induced by this coil if it enters this magnetic field of 2 teslas in 3 seconds. So we know that, so let's first of all write out our formula. EMF is equal to our change in flux over change in time. Now, we need to figure out, so we know that the change in time is 3 seconds, that's good. We need to figure out our change in flux, right? So our change in flux is going to equal to our flux final minus flux initial. So what's my initial flux? Well, my initial flux is when it's sitting outside here, there's no magnetic field, so I probably should actually write B final, A final minus B final, B initial, A initial. Well, my initial area, my initial magnetic field is 0 because it's sitting outside, so 0 times anything is 0. So this is going to become 0. So what's my B final? Well, I know the magnetic field in the end is 2 teslas. And let me find the area. Well, the area is going to be 20 centimeters by 80 centimeters. I mean, remember, we have to use SI units. It's 0.2 times 0.8 is going to, and that is going to give me 0.32. And the unit for flux, if you haven't seen my video before, is Webers. Now let's go on to this this equation. So I'm going to have 0.32 over a period of 3 seconds. I'm going to have 0.1 volts. Right. So EMF, because it is just voltage, it's still measured in volts. Right. So the EMF that we induce here is 0.1 volt. Okay, so let's have a look at this question. So we have a ring placed in a magnetic field that increases from 2 teslas to 5 teslas, and it took 0.004 seconds. The ring is of 0.2 radius. Determine the EMF induced. So we know that the formula for EMF is equal to change in flux over change in time, right? And so we're going to have, and so let's figure out our change in flux first, right? The change in flux is equal to flux final minus flux initial. And that's going to equal to B final, A final minus B initial, A initial. And so our final magnetic field strength is 5, and our initial magnetic field strength is pi times r squared, which is 0.2 squared, minus 2 pi times 0.2 squared. And let's see, what does this equal to? This equals 0.377 Webers. Let's sub back into this formula now. And the time that this took was 0.004 seconds. My voltage is going to be 94 volts. That's pretty big. Awesome. Let's have a look at this question. So a coil of 10 loops of wire, which have a radius each of 10 centimeters, is placed inside a 1 Tesla magnetic field. This coil is then squished. So what happens is, if you imagine you just squish it, so you just kind of step on it, right? Such that there is no more area. Determine the EMF induced. So we can do, once again, EMF is equal to change in flux over change in time, where the change in time is 3 seconds. Let's figure out the change in flux over time. So we're going to do B final, A final minus B initial, A initial as before. And that's going to be 1 Tesla times pi r squared, which is 0.1 squared, minus 0, which is going to give me... So if we come back to our formula, change in flux over change in time, the thing is, this thing that I found here, this is the change in flux only for one of my 10 coils. I have 10 of them, right? And so they're each going to generate a little bit of EMF, right? They're each going to generate a little bit of EMF. So I actually should multiply this change in flux over change in time by n, right? N being the number of coils that I have. If I have 10 coils, the EMF generated, each of those coils is going to generate, let's say, 0.2 volts. So I do 0, and there's 10 of them, so I multiply by that by 10. So the overall voltage is 10 volts, because each of them generates the same voltage. So I'm going to say 10 times 0.0314 over 3 is going to give me 0.1 volts. From all of the 10. So that means each one should have only generated me 0.01 volts, but because I add them all together in series, it's 0.1 volts. I hope you guys enjoyed the Faraday video. Now, what's more important than Faraday, and the one that confuses people, is Lenz's law. So Lenz's law is coming up next, where we go through the direction of the EMF and the current that's induced. So stay tuned for that. Also, there's going to be an advanced Faraday's law, which is for students who want to explore a bit more detail about Faraday's law. Thank you, and I'll see you soon. We offer physics, chemistry, and math tutoring. For more insightful explanations like this one, head to tutorgum.com.